All right, so before we do the recap, I just want to make a correction just about the regular expression to epsilon innovate that we spoke about 2 lectures ago. I realized I created some inconsistency about the recursive case. I'll correct that right away so you can make a notes. Okay, so the slides I'm talking about is slide number 53, okay, over here, about the concatenation. Okay, over here. Okay, I'll tell you exactly what the correction is. So this is the case that I spoke about earlier. So I said in order to really do the translation from, let's say, if you got R followed by S, you're going to draw the pattern for R and pattern for S. Of course, you got to connect them using epsilon. But I also said you're going to create some extra start state and some extra accept states. That one there, strictly speaking, is not really incorrect because it's still like a valid epsilon innovate. However, it's just inconsistent with the textbook I adapted, so I would like to correct it so we can follow just like the slides. Okay, so the correction would be, let me write it down. So basically, you're just going to remove this part over here, okay, just this part, and also remove the extra states that we have over here. So the idea would be if you actually got a epsilon innovate just for the first regular expression R, you got another epsilon innovate for the second one right here, right? So you don't really create any extra start states. You're basically going to take the leftmost epsilon innovate, take its start state as the start states overall. And also for this particular epsilon innovate, that'll be the rightmost regular expression S over here. And then you're going to take that its accept state as the overall accept states. Okay, I'll write it down. That's basically something I mentioned actually in the example there, but let me just state it again. Okay. So this will be some correction, right? So this is a correction we are making. Let me just make it a little bit thinner. There we go. Okay, you can think about this is the start states of the leftmost epsilon innovate. So that will be the overall start states. And this one here would be the accept states of the rightmost epsilon innovate. And if you refer back to the exercise that we did in class, you will see consistent, right? Just about not creating extra states in the case of the concatenation. So in the test or in the exam, if I kind of ask you to really follow the rules that we cover in the class, you got to make sure you follow this, right? So that's about the correction. Good. All right, so let's now do a quick recap from last time. I think the correction will be priority. Just make sure you guys don't find any confusion about it. All right, so last time, that's exactly what we did, right? Last time, this example here. Right, you can see when we are creating concatenation of 1, 2, and 3, the leftmost epsilon innovate, its start state is the overall start states. And the rightmost epsilon innovate, right here, its accept state is the overall accept states, right? Exactly what I just mentioned. And we talk about just this part here. Yeah, just about the epsilon closure, right? Can just show the conceptual idea. If you actually want to go from epsilon innovate and using the subset construction and lazy evaluation to DFA, you just got to make sure you calculate epsilon closure in almost every step. So we spoke about how we can calculate for the epsilon closure. You really want to know about the recursive definition here. You can take a look. And then the example here. And we spoke about if you want to define the delta hat, the generalized transition function for your epsilon innovate. Think about the base case for epsilon and the recursive case where you got some prefix and you got some last character. It's really similar, right? So what I really want you guys to try is to compare this recursive case for innovate and also the recursive case for epsilon innovate to see what the difference is. They share quite a lot in common, right? So we talk about you got Q prime, you got Q prime prime, and also finally you also need epsilon closure. So that's the extra step you got to make sure you do, because in the epsilon innovate we do have some additional step possible, right, for epsilon transition. right? And this part here is just the same. Once you define the delta hat, you can basically take any arbitrary string and see what the resulting set of states would be. If the resulting state contains anything that's actually accepting, in that way, it should be accept states, right? That's something we spoke about. All right. And then that's just part of the exercise we did, and hopefully you guys will give a chance to try about this one here. You can see the solution on the slides. Quick recap. Whenever you actually want to do any state transition, so what you start with is the initial states, the start states, Q0. But do not just list the Q0 itself. You have to calculate epsilon closure, right, in the case of epsilon NFA. So that's why we calculate Q0, the epsilon closure. And then for the subsequent reading of each character in the input string, for example, you got 5.6, you got 5, you got point, you got 6. You got 3 input symbols in total. So for the first symbol, you want to think about, first of all, you just apply the regular epsilon. Sorry, you just apply the regular delta. And then you're going to get a set of states. And for each one of them, you're going to see what their epsilon closure is. So that's the additional step you have to take. Think about this step over here is just the same as if you want to convert from NFA into DFA. And this additional step about unioning the epsilon closure is what you have to do additionally for epsilon NFA into DFA, right? So that's also something we spoke about last time. And I will highly encourage you guys to really give a try how to complete this exercise on different rows. All right, so that's how we build the transition table for the epsilon NFA right here. Sorry, that's kind of transition table for the ultimate conversion into DFA, right? So think about this will be the DFA transition table. Each state over here is what we call a subset states. And we covered that concept already when we talk about going from NFA into DFA. And the start state over here will be the epsilon closure for the start states. And then for each cell over here is going to be calculated just the same way. You have to use the regular delta, as I just said, and then you got to use the epsilon closure, right? So that's something you want to practice as well. And of course, in the actual slides, you got the answer already for here, but in the test or exam, you might either be asked to build a whole table yourself using a lazy evaluation. You should really know when to stop, right? Number one. Number two, you might be given certain cells to really compute and show the detailed step as well, right? It depends how the question may be asked. But you want to be a little bit over-prepared by just going over the whole table yourself, or even build it up from scratch. I think that'll be the best exercise for you. Even better, you can maybe feel free to modify this epsilon NFA here in whatever way you like. Maybe it's going to recognize a different kind of like a decimal number, and then you're going to build the corresponding DFA accordingly and take a look. All right. There are many different exercises you can actually try that out on your own. And discuss with me during my office hour if you want to. All right, and then we started this here about minimizing the DFA, right? So that's something I'm definitely going to dive into in detail. There's one thing I want, okay, so I'll get there once I get there. So we kind of started talking about algorithm itself. I'm going to do a recap very soon. So for today, as I promised, I want to talk about one more thing, about formalizing the subset construction from epsilon NFA into DFA. So there's one slide there. It's quite math heavy. I want to give you a little bit guidance about how to read that, read the different equation. And then I'll move on to this guy here. So there are 3 examples in total about minimizing the DFA. We're going to do one of them together in completeness in class. And then I'll let you guys do the other 2 as exercises. I'll also post the solution a little bit later. So you can give a try for minimizing DFA. It's quite a bit of thinking about how things should be done. But I will go over in detail for at least one example in complete details. Okay? Let me just do one recap over here, just about the epsilon NFA to DFA. So the slides I'm talking about, I'll show to you, is slide 50. Oh, sorry. Bear with me. There we go. 50. All right, so that's the one I want to go over. Slide 50 here. So basically, this is to say if you actually want to, there's a little typo here. There should be a dash, not equal. I just caught that. I'll fix that. So given some epsilon NFA, so you actually got the 5 tuple over here. I'm going to go over them. Right? So given this is the input, and we want to do extended subset construction, extended in the sense that you have to apply the epsilon closure for every step. That's the extension part. And then we're going to do lazy evaluation as well. And the resulting DFA is going to be this. How do we see the correspondence between the DFA as the output and the epsilon NFA as the input? Let's now go over some equation. Okay? Somehow you want to show that this guy here is equivalent to this guy over here. In terms of the expressive power, these two are just equivalent. They can recognize the same set of regular languages, just the same. Okay? So you will see quite a bit of an equation over here. We're going to go over them one by one. Well, something like that, right? All these. Okay, I'll give you a little bit guidance. So let me now switch here, over here. And of course, I would suggest when you were going over these equations here, they are very general, very abstract, very symbolic. Maybe the best way to really see the correspondence is really to take a look at this particular example that we did, right? Think about this is the input epsilon NFA that we have. And this is the corresponding DFA, right? So think about the way to understand it would be. Think about this part here is the epsilon NFA, the left-hand side. Epsilon NFA. And this part over here on the right-hand side of the equality, we basically try to see what would be the corresponding equivalent DFA by using the lazy evaluation, extended subset construction. So that would be the DFA. And also one thing to know, here we're now trying to minimize the number of states in the DFA. It's not guaranteed. It will be another process we're going to apply, right? So here we're not worried about the number of states being minimum. All right? Let's now take a look. The first one here is actually quite straightforward. What about alphabets? Alphabet here is really just the same, just equivalent. So the alphabets for the actual DFA will just be the same as the epsilon NFA. It will just be the same. Okay? If you remember from before, we said that when we talk about epsilon, which will be the extra, like a special transition we are doing, right? That one there is not really a member of the epsilon NFA alphabet, right? Just remember, we kind of mentioned that, right? So that's why the alphabets are exactly the same. Okay? Just the same. And then let's now take a look at the start states. How do you see the corresponding start states? The start state will be, you will simply take the Q0 over here, which will be the start states right here, and then take the epsilon closure, which correspond to exactly this line. This cell over here, right? So we are saying that the start states in the DFA will just be the same as the epsilon closure of the Q0, which is the Q0 here in the epsilon NFA. Right? So that's the second equation, which is not too bad. What about the accept states over here? So this one here also is an equation that shouldn't surprise you, right? That's something we also did quite a bit so far, right? So any states from the NFA, epsilon NFA, where it contains at least one accept states. In that way, it should be considered accept states. Okay, I'll write down the informal description for you to think about, right? Okay, the intuitive meaning over here is any subset states containing an accept states is considered accepting. Okay, so what you want to think about is the subset states over here is actually a states in the output DFA. Whereas when you talk about the accept states right here, this will be something from the NFA. Okay, that's in the input. Accept states. So this is from the epsilon NFA. If that one contains any one of them, so you can see not the intersection is not equal to empty set, right? We spoke about this kind of idea. If that's the case, then that particular subset states should be accepting. For example, you can see here, right? These two, so you can see this is a subset state. This is also another subset state. These two should be considered as accepting in the ultimate DFA because you can see this one here contains Q5. And this one here also contains Q5. So their intersection is not empty. So this is accept state, this is accept state in the ultimate DFA. Okay? Whereas these ones, they don't contain the Q5. Right? So that's about this FD here, about what should be accepting. Right, so this one here is about the actual states. Okay, so this one here will require a little bit of study here. Right, I'll give you some intuitive meaning, and then you want to really see exactly how to go from there. Right. The way to understand this is like this. First of all, you can see it's a set comprehension notation, and then we see it's going to be all the S that's going to be collected together. What will be the criteria for including S? Let's now see. There are two conditions. You can see it's a conjunction here. So you can think about this is conjunction number 1, and this is conjunction number 2. Let's look at conjunction number 1, which is much simpler. Okay. So if you look at conjunction number 1 over here, so the star here tells you that S is a subset states which can be states in the DFA. Not necessarily all the subset states will end up being in the DFA state because they may not be reachable when we do the lazy evaluation. Right, just some additional remark. And what about the green one? Right, so both conditions must be satisfied. And the green one there, I'll put star star. The green one here is more about reachability. Okay, so we say that we should really make sure. So S over here will be reachable in the sense that if we apply the extended transition function from the star states, and after processing W, we're going to end up in this particular states. Okay, there should be at least one string that's going to lead us there. All right, so I'm going to put it here. So here we say that S is reachable from Q0. You can see Q is reachable from Q0 using a string, W. By W. And then with respect to the generalized transition function. So really look into this particular exist over here. So you can see, for example, why are we using their exist, but we are not really using for all? Right? We're just requiring at least one string that's going to lead us there. All right? Rather than all the strings. All right, so that's about, excuse me for my running nose. And then the next one here, so here is about all the reachable states. Let me just say one more thing. So QD over here is about all the reachable states. And the last one. The last one here is about the transition function here, over here. So given a subset states, and then we want to do some read some symbol. For example, given this particular subset states, which can be S, right, it's a subset states. And then we're reading maybe some plus, what will be the corresponding, reading plus, what will be the corresponding states, which will also be a set, which can be empty, could be not empty, right? And the way to do it would be, we start with S, and then we just apply the regular delta. And then, just for S, we apply A, and then we're going to get a set of states, and just collect that. And make sure you actually do the epsilon closure, S prime. Okay? So the way to think about this one here, I'll do a little bit more visualization here. Okay, right here, right? So here, star, star, star. Okay, I'll put it here. What we have is, so let's say we talk about the source. S right here. Oh, actually, I don't need a circle. I need a source S, and then what I'm doing is I'm trying to read the input symbol A. And then that one there is actually going to lead me to somehow S prime. And then from S prime over there, I should also calculate the epsilon closure of S prime, right? That's what I'm having now. Okay, right here. And then it's really corresponding to this visualization here. The visualization here is not exactly precise, but hopefully that'll give you some intuition. Right, so here are some guidance for you to really look into this equation. Of course, in the actual test or exam, you got to make sure the precise meaning is understood. Okay, if you struggle with any part of it, let me know, and then we can talk about it. Okay. All right, any question about this page here? Yes, please.
So the accept states F is going to consist of two
subset states.
The first one contains Q2, Q3, and Q5.
That's correct.
Even though Q5 is the only one that
yes.
makes the intersection or not.
Yes. If you look at the definition here, we're saying for all the DFA itself, its accept states will be all the subset states, number one. So this will be the subset states. Right? It's going to be a set of states here. And then all the subset states such that its intersection with the accept state for the epsilon NFA is not empty. So you're exactly right. So Q5 is here, Q5 is here. So that's why these two are considered as accept subset states. Okay. Yeah. Yeah. Just excuse me for 5 seconds. Okay. So that will be the last part about the epsilon NFA. And then let's now try to do minimization. That'll be the last part, second last part for the lexical analysis. But let's now at least do the minimization here, and then we'll take a short break, and then we can do the last part for the lexical analysis. Okay, good. All right, so let's see where we were. So this is where we were from last time. So we kind of went over the algorithm. Let me just recap very quickly, and then make some additional annotation just to clarify intuition, and then we'll do this example together, all together. Okay, that one involves just a few steps just to get some idea. And then I will assign example number 2 and also example number 3. I can tell you example number 3 is actually more complicated, but I'm going to give you the solution, right? So you can kind of follow through what we discussed for example number 1 and give it a try. And that could be kind of the complexity you can expect in the actual exam. So maybe you can try that on your own. But I'm going to give you a solution later. Okay, so let's now go back to here about the algorithm itself. Maybe before that, let me clarify what a partition is, because I kind of mentioned partition on last Thursday's lecture without really explaining it, what it is exactly. You can think about partition is simply just a set of states. Okay. So given Q is a set of states, let's say we got some DFA with exactly 1, 2, 3, 4 states. And now when we talk about partition, it simply means a subset of the states. Partitions is simply means subsets. All right, let's start with that. And then here, we just want to talk about what would be the smallest number of partitions. Okay? If you're given this, the smallest number of partition will be, you just cannot partition it any further. There's a single partition there, just a single one. Okay? So what we have is, so this will be the smallest number of partition. Okay? So let me call that Q prime. Okay? So Q prime is the smallest. So I got so think about partition itself is actually each partition is actually a subset. So here I got a single partition. And it's going to contain just Q itself. Right? But Q itself is a set of states, which would be basically S0, S1, and then S2, and then S3. So think about this is the only partition, a single partition. So this is a single partition. That's one extreme case. What about the other extreme? What would be the largest number of partitions over here? As you can see, to really reach the smallest number of partitions, the partition itself should be the maximum size. So now if I want to get the largest number of partitions, each partition should be smallest in its size. In this case, of course, we can maybe choose each partition to be of size 1, right? So let's now draw that one there. Let's say here, oh, you know what? Let me just use maybe P. That's the symbol we're going to see in the algorithm. So just to be more consistent. Let's say this is P prime. And this one is P prime prime. Okay? P prime prime. And this one here will be, each state will be in its own partition. So it's going to be S0 is in its own partition. S1 is in its own partition. S2, its own partition. And finally, S3 is also in its own partition. So we got 1, 2, 3, and 4. 4 partitions. And of course, you can also have some partition in between. So it could be rather than one partition, somewhere between 1 and 4. Let's just create one very quickly, right? What if I want to get, let's say here, somewhere between? Let's say P prime prime prime. Okay, so I'll put here P prime prime prime. Let's say we want to get maybe 3 partitions. It could be that S0 is in its own partition. And then S1, S2 in the same partition. And also again, S3 is in its own partition. And then over here, we're just going to get, let's say 1 here, 2 here, and 3 here. Okay, so here we got 3 partitions. Okay. Of course, there are other possibilities as well.
So like it's basically everything that's not 1 or like 4 partitions.
Yeah, of course, if you want to enumerate all the possible partitions there, the size, the cardinality of each partition can be different, right? I'm just saying the number of partitions could be 1 or the cardinality of its the actual set of states and somewhere in between.
Also, if this is subset, shouldn't like the empty SQL?
No, normally when we talk about partition, we don't say like an empty partition, because in that way you're just introducing like an infinite possible number of possibility. So we don't talk about any empty. Okay, so you can think about non-empty subset. Okay. All right, so that's about partitions. We're going to actually need partitions very badly, so that it's good to clarify just about using example to see what they are. Okay. All right, let's now go back to the algorithm. I want to make a little bit more annotations, and then we can do the examples together. Right? I want to just draw some diagram to kind of show to you. Okay. Right, this is where we were from last time. Okay. One thing that's really important for you to see, right? Again, we got input, which is a DFA. We got output, which is another DFA. They might be the same. In which case, there's basically no optimization that could be done. Okay. You will see that we got P and T over here, and also we got P and T over here. You will see some funny, in some ways, I think it's a very common programming pattern. So you can see in the beginning, P will just be empty, and T will be the 2 partition we start with. So for this algorithm here, we start with exactly 2 partitions. Accept states versus non-accept states, exactly 2 partitions. Okay, partition 1 and partition 2. Okay, so that we got P and T, and then we got some while loop. I will explain this in just one moment. And every time before, in the beginning of the loop, we're just going to assign t over here to p. Right? T here to p, first of all, and then we say t should be empty. We kind of reset the t. We reset the t so that we can calculate t from scratch to see what it ends up being at the end of the iteration. If it turns out this condition here, let me talk about a while condition. Okay, I want to speak about the while loop. Okay, I want you to take a look at this one here. Okay, I'll make it a little bit larger for you to see. Okay. If you look at the while loop here, we're saying that as long as p is not equal to t, then we got to keep doing the optimization. That means as soon as p is equal to t, that means the last partitions we have done is now just the same as the current partition we have done. So that means the number of partitions we have done so far cannot be improved anymore. So no more optimization. Okay? So let's now write it down over here. So the while loop, you want to think about, we exit from the loop when p is exactly equal to t. Okay, and you want to go a little bit further here just to annotate. So the t here is the results from the current iteration versus the p is the result from the last iteration. If the current and the last iteration will just give you the same result, that means no more optimization can be done. Okay, and the p here is really the result from the last iteration. So that is the result from the last iteration, right? And especially you want to see that t here is being used right here to keep, is going to be keep updated. Another thing you want to also notice is, this is a while loop, that's outer loop, and then we're going to say that p is the result from the last iteration. And then from the last iteration, we're going to go over each of the partition. Think about, for example, let's say p here, the capital P, could be, let's say, this one here. Let's say, for example, this can be the capital P. And then we got to go over each one of the partition here to see if we can further partition them. If we cannot, then this should be the final partition we should really adopt. Okay, so that's something you want to notice that as well. So this algorithm here is really a nested loop. We got two loops basically. So we got outer while loop, and also we got the inner for loop. And then I'm going to mention another term for you guys. You may have heard about it maybe in other math course. So look at this one here. This one here tells us we should really re-examine each partition from the last iteration. Examine each partition from the last iteration and try to see if we can make any further improvement. And then this line here is very critical, right here. Okay, I'll get there. Let me see, how about this one here? This line here is actually very critical. For each partition that we are considering, we want to see, can we further partition this partition? Let's say, for example, if I'm currently considered this partition over here, can I break it down into two separate partitions? If I can, I should do so. That's why you will see another helper function here is called splittable, right? That's something we're going to talk about, maybe using an example. How do you understand about this particular splittable, right? I'll take a look. So you can see splittable, which I kind of explain intuitively what it is about, right? Let's now take a little bit more like a closer look. Whenever I try to splittable, I got two input over here, okay? So think about splittable here. So P here is the current partition being examined. Remember, P here is going to be each partition. P is going to be each partition in the capital P, right? So now I'm talk about lower P. Okay. And S over here is going to be some proper subset of P. So let's say, for example, if somehow I'm given this particular partition P, little p, if I'm able to somehow show that I can somehow group this is as one partition and this is another partition somehow, I'll show you exactly how. Then this S0, S1, S2 here is a proper subset of the original partition. In that way, I can split this into a separate partition, S0, S1, and then S2. And then this S3 will be just another one. On the other hand, if somehow I realize that the best way I can do is to still have this as a whole. In that case, it's not proper subset anymore. So that's why the proper subset here, you want to notice that is very important, right, when you study. Okay? And this condition number 2 here is also very important. Let me visualize it for you. Okay? I'll try to do that. So think about we have this. So I'm going to draw some partition here. And we're going to do example very soon. Okay? Let's say if we have, let's say, 2 partitions. I got partition little p, and the little p here really corresponds to the little p over here. Okay? I got p here. I got another different partition, p prime. Right? So here, this is the partition. And this is just another partition. I got 2 partitions over here. Now I want to see whether or not I can somehow split a subset from P out. How can I know that? Right? That's something we're going to keep doing, going to do the example. Conceptually, if I'm able to find a proper subset over here. So let me draw that proper subset. Let's say it's a proper subset, cannot be the entire P, cannot be, it's a proper subset. Let me call that S. It's a proper subset. If somehow I can show that somehow if I try to do certain transition using the same input symbol, let's say C, let's say, that's kind of the C you will see here, right? If every state in this particular subset of states is going to lead you to the same subset state in another partition, that means we can split this out. Okay, that's what it means. So this one here is just going to be another subset state over here, and then it's going to be S prime. Okay, so what's really important here is our goal is to show that S is splittable from P. How is that possible? If somehow we try to make a transition using the input symbol C from all the states S, it's going to lead us to all the some states in the same partition P prime. However, P prime is not the same as P. If that's the case, then we know that we can split S out. If we cannot find that, we cannot split it. So this is something we're going to keep doing when we solve the example. Okay? Okay, one more thing, and then we can do the example. When you actually look at the while loop over here, we said that we're going to exit when P is exactly equal to P. When P is exactly equal to T. That means whatever we're doing from the last iteration, and we try to do one more, whatever we did from the last iteration, and we try to run one more iteration, but we get the same result. So that means we shouldn't really keep doing it. Otherwise, the loop will not be terminating. So there's another term for this. That means we have reached a so-called fixed point for the iteration. Okay, so we say we exit when reaching a fixed point. When last iteration result is exactly equal to the current iteration result, fixed point. So fixed point is just for your information, right? Sometimes when people want to talk about like an iterative or recursive algorithm, how do you actually characterize the termination? You can talk about some fixed point, but that's beyond the scope for this course. Okay? All right, quite a bit of annotation here for the same algorithm, but it's something you can revisit and try to see each one of them. It would make sense.
Sorry, can you explain the board quickly?
Explain what, sorry.
Splittable
Which part of splittable? You mean conceptually?
yeah.
So splittable is more like a Boolean, true or false. Given some partition, can I split a proper subset of P, which is called S? Can I split S from P? Can I or can I not? I can do that if, number one, S cannot be the entire partition. I cannot split the entire partition out of itself. I can only split a proper subset from that. So condition number one is there. Condition number two tells me that, let's say given that S is a proper subset of P, I can only split it if every state in S, by taking some symbol C, is going to lead me to some states in a different partition. If that's the case, I can split it. You will see some concrete example in a moment. Yeah? But think about all the destination states by taking C is going to be just part of the P prime, which is another partition. And P prime here cannot be the same as P. All right? Okay, let's now do the example quickly. Okay? You know what? How about this? In the interest of time, it's already about halfway. The example wouldn't take that long. Why don't we take a very short break, get yourself fresh, and then we'll do the example together. Okay? So why don't we take a short break by taking attendance. All right, let's now do this example together. I kind of started with the very first step, just about what will be the initial partitions we have, right? If you look at the algorithm, it's actually going to be the accept states and also non-accept states, right? For now, let's not worry too much about P and T. I'll show you exactly what you should do in an actual test or exam scenario. But I'm going to show you some tracing table you can also try to complete just to further strengthen your understanding about the actual algorithm. We'll do that a little bit later. Okay? So this will be the initial partition. Okay? Accept states and also non-accept states. And we also, oh, by the way, we also spoke about last time about how to understand about the SE, right? So that one you can refer to as well. Okay? You can double check. Okay, so let's now say we got this initial partitions. We got one partition here. We got partition number two over here. Partition number one will be all the accept states, S3, S5. You can see double circle. And we got partition number two will be everything else. Okay, so that's why for the partition here, we got exactly this and this, right? But let me just erase this one here. We don't really need that for now because I already colored all the states as partitions. So now we want to see splittable, basically, right? If you remember what we saw in the algorithm, we say that we're going to go over all the little p, capital P. Think about the capital P contains this partition over here and this partition over here. And then the little p will be either this or this. We can look at each one of them to see if we can split some subset or proper subset states from there. We're going to go over this one here first to see if we can split anything out. And we're going to go over this one here and to see if we can split anything out. That's the plan. Conceptually, you want to go over all the partitions. Okay? And to make it more efficient, you can see that here we got input symbols F, E, I, E, etc. So we can only focus on the symbols that are already present because everything else will just go to the error state, right? So let's focus on those. So what we're going to focus on will be the input symbols. Let's say input symbols to focus on. That will be F, I, E, and also everything else, other. All right. Let's now start with the first one. Let's say if I choose F. And let's say I would, for now, I'm just focused on little p, which would be the pink. Okay. So let's say this one here is going to be my partition to focus on. Okay. Let's say this one here. So this would be the little p, lower p. And then if I consider the input character F, think about what's happening here. Where can we find the transition for F? Either we can say S0 here, if by taking F, it's now going to lead me to the same partition. So it's not splittable. SE here, if I take F, by definition, it's all going back to itself. It's error states. So it's also going from SE back to SE. So in both cases, we are still staying in the same partition. So that means for F over here, no split. Okay, for the very first one, I'm going to write it down in detail. Okay. So if you consider the input character F, you got two cases. Either you got S0 itself, and then that one there is actually going to give you to S1. And this one here, if you try SE, that one there is actually going to just itself. So you're basically just going from the pink partition to itself. So no split. All right. So that's for F. And similarly, you can also give it a try on yourself. You can think about for I and also other, no split. So all these have no split. So in the case of running processing F, I, and other, we just have no split so far. Okay, no split. And then we're going to consider what's really missing here is about E. All right, let's talk about the E. So if I look at the E here, okay, so there are two cases for us to consider, for example. For E here, you can see I can go either from S2 or S4. And then it's going to lead me to either S3 or S5. I'm basically going from here, which is a proper subset. And it's going to lead me to another set of states which belongs to a different partition. So that's exactly what splittable is going to hold. All right, I'll write it down. So that one there is going to give me, for example, S2, S4. S2, S4 is going to lead me to, by processing E, is going to S3, S5. Okay. And if you think about S2, S4 is in the pink. And it's going to lead me to S3, S5. So now I can split S2, S4. And notice that this S2, S4 over here is a proper subset. It's a proper subset of the little p, right? Right here. So it satisfies both splittable conditions. There's another one there you can also take a look. Let's say we got S0. Let's see over here. Yeah. S0, S1, and also SE, right? So for example, S0, S1, and also SE over here. S0 is only defined for F. So if you got E here, it's going to here. S1 over here is simply just going to S2. And then SE over here, if you take E, it's just going back to itself. So in all cases, it's just to the same partition. All right. That one there is simply just going to go to basically the same partition. And you can fill out the states. Okay. So this one here is not splittable. Not really. Only this one here is splittable. Okay. So I'm just going to say this is splittable. So that one there is splittable. Okay. All right, so what should we do? What we do is, let me now copy the diagram. Okay, I'm just copy that. And then we're going to reach a new partition. The same state over here, but we're going to somehow color them a little bit differently. S2, S4 cannot be split into a separate partition. And everything else remain the same. So I also got SE, right? Okay, let's just write it right here. Okay. So for that one there, I actually got S0, S1, and also SE. They remain to be in the same partition, but we may have to look at them again. And also we have S2, S4. This one here, this one over here. And also we got S3 and also S5 right here. So we used to get only 2 partitions, but now we got 1, 2, and 3 because we split these 2 states into a separate partition. Okay? And for number 1 over here, little p was this, and then we split this out. And remember over there in the algorithm, we got to show for little p, that's a member of capital P, right? So there's another one we should also consider, which is this, where little p is actually S3 and S5. That there's actually no transition. Right? You can think about S3, S5 is just going to, okay, I'll show it to you. This is also important to show to you. So let's say here, when little p is actually equal to S3, S5. This one here is actually very interesting. Okay? If you think about it, these 2 are the accept states. Implicitly, if you're trying to maybe do any input symbol there, they will all go to SE, right? So you might be thinking, S3 and S5 are green partition. By taking some input, for example, A here, both of them are going to SE, which is a different partition. Aren't they splittable? The answer is no, because it violates the subset condition right here. All right? That's something you want to avoid. All right? Okay, so here you want to do something like this. So we got S3, S5. And then if you actually try to take any transition, okay, anything. So if you take any C that's in the sigma, right, can be anything. And then it will simply bring you to SE. Okay, so this one here, which is green. And then it's going to lead you to SE. So even though you're going from green to pink, but the problem is this one here is the entire partition here. So that wouldn't satisfy the splittable. Okay, so this one here is actually not a proper subset of S3, S5. So that means it's not splittable. Okay, this is actually very important. Otherwise, you might just get yourself confused about why are we not kind of split these 2. Well, if you split these 2 into a single partition, you just end up being the same thing, just different color, right? All right, let me recap very quickly about the first one, because for the remaining step, we can do a little bit more quickly. For every step, you got to make sure, given however many partitions you have, you got to make sure you want to go over each partition over here and try to identify any splittable maximal subset states. And then, in this case, for the pink one, we identify S2, S4 being the subset. That's maximum for us to split from there. So that's why we got a new partition. For S3, S5, we cannot split the entire set out. So that's why it's not splittable. All right, so we actually have seen both cases. All right, any questions? It's not trivial, right? It's definitely tricky. So, but I think just going over some example, you got some exercises, and also you want to revisit the algorithm as well, right? It's actually all important. All right, so now we are now in step number 2. Right here. Okay, we used to be step number 1, and now we are in step number 2. Right, in step number 2, I'm going to go directly to the one that can be split. Right, I'll just write down something for you. Again, you should really try all these possibilities. Right, so what you would do is, so you're going to say F, no split. And to really justify, you will justify in a similar way, like these. I'll leave that to you. Okay? Similar, because if you can see, if you take S0, it can only lead you to S1. If you take SE here, by taking F, it's also going to lead you back to SE. Right? It's no split. Okay? And we can take a look at I can tell you. Okay, for I over here, right? So there are two cases we can consider. Let's consider something that's splittable. If I try S1 here, you can see if I take I here, I can go to S4. And S1 is a proper subset of the entire partition. So that one is splittable. It's just a singleton set. Okay? So what I can do is I can say for I here, I got basically S1, and by taking I, and then I will simply go to S4. So I basically go from, I go from pink to blue. Now I can split S1 out. So this is splittable, right? So think about this one here is splittable. It turns out this is the only one. Let me just take another example, right? What about, for example, here you can see S0, SE. If you take the same I, S0 taking I is going to be here. SE taking I is going to be itself, still from pink to pink. So not splittable, right? So here, if I do, for example, S0, S1, S0, S1, and then if I simply take I here, it will just lead me to SE. And both of them are the same partition, not splittable. Not. So it turns out this is the only splittable states, right? What's that going to be? Let's see. Okay, I'm going to copy this one here. Okay, now we got number 3. Okay, I'll put it here. So I got number 3 over here. And then I'm going to split S1 out, right? Remember, we got S1. That's the only thing that's splittable. In that way, I'm going to just put S1 right here. So if you compare, when we go from 1 to 2, we split these two out right here. And if you compare 2 and 3, we split this one out. All right? And now, if we want to run this another iteration for this, we got to consider, can we split anything out from here? Can we split anything out from here? That one is actually no-brainer. You cannot. It's a singleton set, right? Can we split anything out from here? Can we split anything out from here? Right? That's what we got to check one by one. And for this iteration here, it turns out it is possible to split this one further. Okay, I'm going to show to you directly. Okay. So you can think about this one here would just be the little p that we have. Okay. This one here would be the little p. And then, you can see that S0 here, if I take F, I can go to S1. I go from pink to orange. Of course, I can split it, right? But for SE over here, I take anything, it will just go back to itself. Still go from pink to pink. So no, it's not splittable. All right, so I'm going to put, if I consider just F over here, so now I can go from S0 by taking F. I will go to S1. So I'm basically going from pink to orange. Right? So this one here is splittable. And this will turn out to be the last split we have to do. But just give me a moment. I'll give you another example here. For example, if you do SE, as I said, if you do SE over here by taking the same F, that one there is not going to give you any split. Because SE itself, taking any input, will just go to itself. Right? So you still go from SE to SE, not splittable. It is not. All right, so what will be the last one? Okay, the last one here, let me just copy that. Okay, so copy this diagram here. This will be the last one. Okay, so this will be number 4. And then let's now put it here. Okay, oh, sorry. Okay, right here. And then we're going to split S0 out. Right, you can see that's splittable, right? This one here. Okay, if we split S0 out, we can use another color. So let's say we use a purple right here. And if you want to run another iteration, it will turn out you got to check this partition, this partition, this partition, this partition, and this partition. None of them is splittable anymore. So you reach a fixed point. And the algorithm about minimization terminates. Not splittable for any partition anymore. So this will be the ultimate result. But you might be wondering, okay, so this is, we should use coloring. What's the corresponding DFA? Let's do that step as well. Okay, I'll do that in a separate page. Let's copy this one here. Okay, it's a little bit like a subset idea that we spoke about earlier. In the minimized DFA, every state there is more like a subset states. Okay, so this is the minimized This is the maximized number of partitions. Maximum number of partitions. That one is going to give us the minimum number of DFA states. That's appropriate. But now we're going to see exactly how we can turn this one into a DFA. And the way to do that is, you can think about each one of them is a subset. This is a subset. This is a subset. That's one, and that's one. All right? Let's now do that. So I'm going to get one subset state called SE. Okay, I'm going to put it here. Okay, let me draw that first. And then I also got one subset state for S0 by itself, which is purple. I'll draw that. And also I got another one, which is S1. And then I got another one, S2, S4. And finally, I got S3 and then S5 right here. And since these contain some accept state from the source DFA, similar idea. Since the intersection of this and the original accept state is not empty, so that should be the only accept states. Okay, right here. So that's why I draw a double circle right here. Okay, let me just color that, and then we'll see how to draw the transition accordingly, and then we're done for this example here. So we got SE right here. We got S0. And then we got S1. And then we got S2, S4, another partition over here. And finally, we got S3, S5. So now, how do we figure out the transition, right? So what will be the start states? The start state will be basically this one here, S0, right? It's original start states. So we'll start with that. Okay, from S0, you can see that if you take F, you're just going to go to S1, right? If you take F, you'll just go to S1. And then if you take maybe anything other than F, you just go to SE by definition, right? So the way to express would be, for example, I can say to go from S0, if I take anything other than F, you can say whatever the sigma is, set difference F. is going to lead you to SE, right? So now we cover all the possibilities, right? And I'm just going to complete the DFA. You can double check later, okay? So what about going from S1 to, for S1? If I try to go I or E, you can see S1 here, go for I or E. I'm going to go to this state here. Anything other than that is actually going to the error states. Anything other than that is going to be sigma I and E. All right? And then this one here is going to be, if I go from S2, S4, I can take E, right? S2, S4, I can take the same E. I can go to this partition here. Anything else would be error states. Okay, I can do that over here. Okay, this will be sigma set difference and then E over here. Okay, what about S3, S5? S3, S5 is already accepting, right? It doesn't take any other input symbol. So anything is going to lead you back to here, right? So that one there is going to be basically like that. Anything that's in sigma. Okay. Okay, I believe I got everything here. Yep. And of course, for SE, anything that's in sigma just going to lead back to itself. Okay, so that's the resulting DFA that's guaranteed to be the minimum number of states. So if you consider the input has 1, 2, 3, 4, 5, 6, 7. 7 states. And this one here, 1, 2, 3, 4, 5, 5 states. Yeah, roughly speaking, you kind of save 2 divided by 7, it's about maybe, what is that? Roughly, about 30% reduction, roughly. Right? We kind of reduce 2 states over here. Right? It's a very small DFA, so just for illustration. But if you actually got a larger scale of the DFA, you might be able to see kind of appreciate the algorithm can give you kind of a reduction on the number of states. All right? All right, any question about this? All right? Yeah?
You mentioned last class that the going back to the error states are optional for the epsilon NFA.
This is not epsilon NFA. This is DFA.
Right, so for the DFA, it's not optional.
It's not optional anymore. That's correct.
We also don't put the epsilon going to the start state.
We don't have epsilon because this number one. This is DFA. It's not even NFA. It's not epsilon NFA. Right? So we have to make sure for every state here, we got to consider all the possible input for exactly once. So there's no non-determinism. Yeah. Okay. All right. So for you guys to do as exercise, so this will be example number 2, which is a little bit easier. And this one here is more complicated. I'll suggest give a try. I will possibly release the solution maybe during the reading week. So give a try, and then you can click on the solution and see how that one is going to turn out to be, right? Yeah?
Quick question. How do we get the initial partitions? Are they just the final states?
Yeah. Okay, how do we get an initial partition? Good question here. If you refer to the algorithm over here, you can see that the T here is simply just the accept states and also all the states minus accept states. Accept versus non-accept. Okay. So if you look at the example there, we simply got accept, non-accept. That's where you started.
So like in example number 2, the only set of states is E0?
Yeah, exactly.
Okay.
Yeah, exactly right. Which might make this example quite easy to do, but I'll leave it to you. Okay, think about it. Yeah. And of course, for this one here, it's going to be different, right? Initial partition will be, let's say these 3 will be in one partition. The remaining ones will be in another partition. Yeah. Good. Okay, we got about 6 minutes. I think I just got one more example there to really put everything together but I think that one there is going to take a little bit of time. So basically, this is one more example which I can spend about 10 minutes on Thursday. So this will be the last example, last thing to really put everything together. Let me just give you some intuitive idea, and then we'll go over in detail on Thursday in the beginning. So far we have talked about, regular expression, DFA, NFA, epsilon, NFA, and to see how we can do the conversion in between and also minimizing the DFA, right? So now, all good. Let's say this is kind of the minimized DFA transition table you have, right? Now we want to somehow see how we can implement a scanner to do the lexical analysis, which means we're going to take some input string W, character by character, from left to right. Eventually, we want to somehow say either success or we're going to say fail. If success, we're going to return some token by token, right? That's kind of what we said earlier when we talk about lexical analysis. So on Thursday, I'm actually going to go over with you this kind of like a little bit low level algorithm about how to implement a scanner. Number one, we have to understand this algorithm here to really appreciate how it can be done. So we can, once we get a list of tokens, we can actually use them to do the next phase, which is about syntactic parsing, number one. Number two, luckily, in reality, you don't really have to implement this tedious thing yourself. All you got to do is, if you specify regular expression like this for your different tokens, maybe for keyword, for maybe some identify, etc. Once you specify the regular expression, and then you specify this in enter for, it's going to generate something like this for you automatically, and guarantee the DFA is minimized in its number of states, right? But in the lecture, as we said, we're going to learn about the theoretical foundation, about what's being generated for you. All right, if no objection, we can finish a little bit earlier today, just a few minutes. But on Thursday, as I said, I'm going to go over this algorithm here in detail. Wouldn't take long. And once this is done, we can move on to syntactic analysis. And you guys can also take a look at the slides. It's really about context-free grammar, etc. Okay, I'll see you on Thursday.